Hi everyone, and welcome to today's webinar, which is Understand More Using the Advanced Modelling Features of LimitState Ring. It's the fifth of our regular webinars that discusses the features and application of LimitState products. My name is Tom Pritchard, and shortly I'll be passing you over to our speaker for today, who is Professor Matthew Gilbert. The session is going to provide you with an insight into some of the less well-known features of our Masonry Arch software, LimitState Ring, such as how to diagnose the likely causes of existing transverse cracks, how to identify potential load paths under service loads, modelling specific defects such as partial ring separation, and also how to model the presence of discrete reinforcement. The main section of the webinar will run for about 30 to 35 minutes, and there will be some time at the end for questions, which can be posted at any time via the question functionality that's present in the interface on your screens. As always, we do try to answer as many of your questions as we can. Sometimes time doesn't allow this, so apologies in advance if we're unable to get around to yours. We will, however, follow up on any unanswered questions after the webinar is finished, and if it does spark any questions later on, then please do contact us on info@limitstate.com, and we'll be more than happy to answer those in detail for you. So without further delay, as I said earlier, our speaker today is Professor Matthew Gilbert, who is the LimitState Ring Product Manager, and I'll pass you over to him.
Thanks very much, Tom, and thanks very much to everybody for joining us today. Okay, so first of all, I'll just give you a quick rundown what's in store for the webinar today. I'll just say a very few words about the company, LimitState, then move on to a bit of background to Masonry Arch bridges and how we go about modelling them. And then I'll dive into the specific emphasis of today, which is the advanced modelling features that Tom mentioned. So three key features. One is using the support movement mode to identify load paths under service loads and also the causes of cracks. Secondly, modelling specific defects in a bridge. And thirdly, modelling discrete reinforcement. And then I'll wrap up with some conclusions. Okay, so first of all, just a very few words about LimitState. It's a company set up almost 10 years ago. We're celebrating our 10th anniversary this autumn. But our focus has been primarily on developing tools to analyze the ultimate or collapse condition. And the reason we focused on this is because we see there being a big gap in the market. So at the moment, traditional techniques such as slope stability techniques for major class of geotechnical problems have been of a hand analysis nature at the one extreme, and then at the other extreme we have very advanced, for example, finite element based techniques for the same purpose. So there's been a gap between those types of tools. So ones which can be done by hand or on a spreadsheet or simple program, and those that can be done using an advanced modeling technique. And the same applies not just for geotechnical problems, but also for masonry arch problems, and also for example, concrete slab problems. So the gap that we're filling is with what we see as being mainstream numerical rigid plastic analysis techniques. And mentioned three applications, surprise, surprise, LimitState have got three products which focus on those three applications, so masonry arch bridge analysis software, geotechnical analysis software, and concrete slab analysis software. And these tools are now widely used in more than 30 countries worldwide. Just as a slight aside, we have actually a couple of weeks ago launched a new product called LimitState Form, which uses many of the same mathematical techniques actually for design problems. However, it's targeting primarily sort of aerospace, automotive in the short term, so I won't bother you with further details now. So here's a brief list of, or a partial list, should I say, of customers. So starting with A and moving down as far as B. So you see some big companies there, also some local authorities and smaller companies as well. So it's popular tools for use in the construction sector. Okay, so moving on to a bit of background. First of all, what do we know about masonry arch bridges? Well, we know there are a lot of them. There are probably about 1 million spans worldwide, and the vast majority of them are well over 100 years old. Very often we're still requiring them to carry heavy vehicles, and hence we need to assess them. However, when we come to assess them, we often find unique details. When I say details, perhaps it's a euphemism for unwanted details, defects, mortar loss, spalled masonry, in the case of multi-ring brickwork arches, partial or full ring separation and so forth. So that kind of suggests that we need reasonably discriminating tools when it comes to assessing them. The slide I've often show in webinars as a kind of initial dive into the theory of masonry arches is this one. It's basically using Robert Hooke's hanging chain analogy, and I'll explain in a few minutes why it's relevant to a particular topic for today. But if we look at the analogy, Robert Hooke said if you have a weightless chain or cable, you hang the voussoirs that you're going to use to form your masonry arch from that cable. You look at the profile shown in red, you then invert it, and you can fit that profile entirely within the thickness of the masonry, then your arch will successfully stand. But the key thing is there are lots of profiles or lines of thrust that also fit entirely within the masonry. And that's because a classical masonry arch is a statically indeterminate structure, so without knowledge of the initial stress state, etc., and the material properties, it's basically impossible to know exactly what the particular line of thrust is, unless you are looking at extremities. And one possible extremity is when you have a large, in this case, eccentric load on the structure, such that you transform the masonry arch into a mechanism. At that point, the line of thrust is uniquely determined, and we can also work out very easily what the maximum load is, or what the load required to cause that behavior is as well. Similarly, and this is relevant to today's webinar, if the abutments, for example, were to move relative to each other, for example, outwards or inwards, again, that means that we can have knowledge about the line of thrust, so it's uniquely determined, and hence we can gain an understanding of how the load is transmitted through the structure. So just some key points. If we were to have an applied load on our arch, we know there are lots of possible lines of thrust. If the supports move, we can identify a unique line of thrust, and we can effectively explore this with the support movement mode in limit state ring. Similarly, at collapse, we have a uniquely determined line of thrust, and we can calculate the load at that point required to cause collapse. And that's the normal mode that those of you who've used the software will be most familiar with. So what the software is doing is it's effectively ramping up the applied load until the point of collapse is found. Ramping up in mathematical terms, intrinsically it's part of the optimization process. So how does the software work? Well, as I said, ramping up the load. Basically, we're maximizing the load or load factor subject to equilibrium constraints and also yield constraints. So if we zoom in onto a particular block in our software model, then we know that we have forces acting, so the self-weight of the block, for example, and we also have contact forces applied at every interface. So the equilibrium is just simply saying that we must have equilibrium in the X, Y and rotational sense. The yield condition is saying that for example, the shear force is limited by the coefficient of friction and the magnitude of normal force. And also the moment is limited by the value of normal force and the thickness of the masonry. That's for rocking and sliding respectively. And the nice thing about it is it's a very simple linear optimization problem that we can solve very easily. And what I'm going to do a little bit later is contrast this formulation with the one that we use when we have a support movement condition. Okay, so we've talked about masonry arches. However, a masonry arch bridge isn't just a masonry arch, it's also comprises soil material, potentially internal spandrel walls that surround the masonry arch barrel. The way we model the soil in LimitState ring is quite simple. We surround our masonry arch blocks with backfill elements, and the backfill elements take no load in tension, but they resist movement effectively of the arch blocks into the surrounding soil using this force displacement curve that you can see on the screen. The magnitude of the force is obtained using a modified version of retaining wall theory. So in the model you can see at the bottom, we can see that when we load the arch or load the bridge to failure, we have a 4-hinge mechanism. In the region of the arch closest to the load, so region of the bridge and soil close to the load, the backfill elements are inactive. Remote from the load, they're active, and they're providing passive resistance to the movement of the arch barrel. And then this shows the on screen now the kind of things that you will see when you're using the software. So we see backfill elements. We also see a line of thrust or zone of thrust whose thickness is a function of the compressive strength of the masonry and the magnitude of the normal force. We also see a loading vehicle with dispersed loads, and we can also see blocks and contacts quite clearly, and hinges highlighted in red. Okay, so that's a sort of a very quick introductory description of the software and how it works. Now move on to identifying load paths and the causes of cracks. So as I mentioned at the start, we explore both of these two issues using what we call support movement mode in the software. So we use it to help understand how the structure carries working loads or service loads, and also we can use it to diagnose the causes of cracks. If we go back to the mathematics, what we were doing before was we were ramping up a load, so maximizing a lambda, a load factor, subject to equilibrium and yield. What we're doing in support movement mode is very similar, but instead of maximizing a load, we're actually finding the minimum energy solution, minimum energy configuration, and what we have is an unknown support reaction, and we are basically using the principle, we're using an energy relation to, as you can see in the middle of the screen, but the rest of the terms, i.e. the equilibrium and the yield, remain unchanged. So the mathematical complexity is unchanged, assuming that you're looking simply at an instantaneous displacement of the supports in question. So best thing to do is probably just dive into an example. And what I'll do is, so this is the example I'm going to load up on screen. It's a 3-span bridge with a heavy goods vehicle, so an articulated lorry. And I've already set up the geometry for this particular bridge using the wizard. If we zoom in, we can see the axles, the load being distributed through the fill, and we can also see we've got a semi-elliptical profile with backing elements above the piers. The backing elements are shown in dark grey as opposed to light grey, and those provide more resistance than normal fill material. So what I would normally do is, once I've got a model like this, is just click the green button, solve, and this is in standard mode, normal mode, and what you can see that's happened is that it's increased the applied load on the axles on this vehicle, and it's worked out that if it multiplies those loads by a factor of 3.5, termed the adequacy factor in the software, then we get failure in the way that you can see on screen. So we've actually got here a multi-span mechanism, so we've got rotation of the hinge and hinges also, so rotation of the pier and hinges in both these spans that you can see on screen. Now what I'm going to do now is just take the vehicle off the bridge, and what it's trying to, I've got the software set so that it will automatically try and get a solution when I move the vehicle. And if you look at the solution, it's saying the adequacy factor is locked. So if there's no vehicle on the bridge, then increasing the load of that vehicle isn't going to affect the stability of the structure. So that's why it's telling me the adequacy factor is locked. But what I'm going to do now is go to the support movement wizard. I'm going to imagine that each of the spans of this multi-span bridge have moved outwards very slightly, and that will transform the structure in a way that allows us then to view load paths under the action of service loading. So what I'm going to do is open up the support movement wizard, and what's asking me to do is basically pick support blocks to move. So I'm going to basically pick each of these blocks in turn, and I'm going to just have minute displacements on this, -2 millimeters, and I'm going to choose the next one, have it similar but slightly less. So I have the whole of the left of the structure moving slightly from right to left, and then the whole of the right hand part of the structure moving slightly from left to right. So what I'm basically doing is just moving these horizontally. So we have deformations that you can see on screen, -2, -1, 1 and 2. I click OK, and I now click solve. Now it can find a solution. It's no longer telling me about an adequacy factor, it's telling me about an energy or work value. And if I just use a slider here, I can actually accentuate the deformation. So what's happened, you can see, is each of these spans has effectively spread by a small amount. Actually, the way I set it up, the outer spans are spread by 1 millimeter, and the middle span is actually spread by 2 millimeters. Now you can see the hinges on the screen, and the nice thing about this now is I can investigate what the effect of applying a load, in this case this articulated lorry, is on the locations of those hinges. So what you can see is that the hinges are moving slightly. You can also see actually the line of thrust is getting thicker, so the zone of thrust is getting thicker, and that's because we've got this heavy load on it. So the forces in the masonry are getting larger, and you can see how those hinge positions migrate under the action of the loading. Now, in this case, definitely there's movement of those hinges, but there is at least not reversal of them. So a hinge which starts off as in the form of a crack on the intrados stays largely in that form of it. It may move a few courses from left to right. Okay, so you can basically use this as a way of exploring how your structure is likely to be carrying your applied service loading, and you can do this because you've made the assumption of support movement. Okay, so that's so far so good. Let's suppose that something more major has happened. Let's suppose that this pier that you can see on screen now has actually moved downwards by a significant amount. I can go back to the support movement wizard, and I can, for example, say, okay, let's suppose that has moved down by, say, 200 millimeters, so a couple of orders of magnitude more than before. Okay, so why might I want to do this? Well, most commonly you would be interested in this if your bridge was showing existing cracks, and you're trying to work out what external movements of those supporting abutments and piers must have happened in order to give the particular mode of response that you see in the field. So what you could have said is, okay, I do have cracks in my structure, but they're not of the form that we were seeing before. They're actually the pattern is different. Okay, and what you can do is effectively use the support movement wizard as a sort of forensic tool to actually try to understand what is likely to be the underlying cause. If it's a straightforward vertical settlement, then perhaps you need to underpin your pier, or perhaps you need to find out if there's some long-standing mine workings or whatever. But it's often very, very useful to know the underlying root cause of the cracks that you can see in the field. If I go back to the slides, actually what you can see is you can see a structure that looks quite qualitatively similar to the one that we've just been modeling. This is a free span structure, looks fine. However, behind this tree in the intrados, you can actually see a large crack. And actually, if we go to previous, as you can see, it's probably too sort of bound. Actually, the trees are particularly badly located because there's also a crack in the opposite face of the barrel, and that's because this particular bridge was subject to damage from the Boxing Day floods in 2015. And what happened was this pier settled by about 200 millimeters. And the most visible manifestation of this is probably when you're up top of the bridge and you can actually see the parapet wall clearly quite badly deformed. If I go back to the the model. This isn't a perfect representation, but certainly span 1, the cracks in span 1, you can see on screen, map very closely to what can be seen in this particular bridge. What you could now do is move your vehicle across the structure. Now, what I would caution you against is using the undeformed geometry when you have deflections as much as 200 millimeters. What I would suggest you do is that you actually use a user-defined profile to enter the geometry more precisely. But what you can do is you can see, again, what is likely to happen in terms of the load paths when you have this quite severe deformation to your bridge. Okay, this is another example. Now this is the previous example is actually, I think they're planning to completely rebuild the first arch because of this this deformation. The next example is an example of what's done on the railways when you have bad deformation. Is you keep it in service. So this is bad distortion on a multi-span masonry arch bridge. This dates back to around 1915, mining subsidence. So there were mine workings underneath this particular bridge, which is in the northeast of England. And what we've done in the case of this bridge is we've used the LimitState ring software to try and piece together why the cracks, what external movements were behind the cracks that we can see in reality. And we actually found a very good correlation when we assumed that we have some translation of the right-hand king pier and downward settlement of all the other piers and abutments. So very close representation. In this particular case, we did use the deformed geometry in the analysis. So we modeled the as-is geometry rather than what we believe to be the as-built geometry. Interesting thing is we found that the influence of the distortion on the load carrying capacity of this bridge was actually very small. So sometimes deformations can look quite worrying, but actually depending on what the particular natures of the distortion that's occurred, they may not be that serious to the capacity of the structure. Okay, so moving on to second of the issues that I was going to raise, modelling specific defects in a bridge. In the software, you can use what's called a new bridge wizard to set up a sort of global properties of the problem, but you can also edit properties using the property editor, which is on the right-hand side of the screen. And we'll look at an example of doing that in a second. Example I'm going to look at is actually a series of arch ribs that were tested in the laboratory. We actually had 4 arch ribs. One was fully bonded, so each of the rings of brickwork had a mortar joint, a strong mortar joint between the rings. The second one, we had a weak mortar joint between the rings. Actually, it was damp sand. And then arches 3 and 4 where we were trying to reconnect the each of those rings, either using headers or using external plates. So the question is, how do we model those this kind of phenomenon? What I'll do is I'll open up a model of arch 1. So this has got the right geometry, and we've got actually a load here which is can be converted into kilonewtons. So the adequacy factor here is 3.98. So basically about 4. 4 kilonewtons in this particular case. So how do I model arch 2? Well, I can model arch 2 by simply choosing to model the barrel with 2 rings of equal thickness rather than 1 ring of, in this case, 215 thickness. So there, I've done the model very quickly. I click solve. You can see that the capacity has gone down from 4 down to 1.47, so about 1.5. So very significant reduction in capacity. And you can also see the failure mechanism and the fact that the hinges are now diffused. Now, what I can do using the property editor is I can model arches 3 and 4, which had some of these locations where the rings are actually glued together effectively. So what I can do is I can find out where the those plates or headers are and then replicate that in the software. So I think the first one was around the 4th course, and there was 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we have another one here, same on this side. There was one at the very crown, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, and then here. So what I can do is I can prevent sliding. I can also prevent hinging, and I could as well, if I wanted to, prevent crushing. So now, whereas normally I have I can have sliding between the rings, in these special locations, that's prevented. So I can now click solve, and you can see that I've got a different failure mechanism and also a different capacity. It's now gone from about 1.5 up to about 3.2. So using the property editor and changing local properties, we can very easily change the behavior of the structure as we wish. Here is actually a photo of arch 3, and the failure mechanism that we get is very similar. This is the one with the headers highlighted, and in terms of the comparison between the predicted and the modelled capacities, actually very close. The case of arch 1, we did slightly underestimate the capacity, but we may have had some initial tensile bond strength raising the capacity slightly in that case. And in the case of arches 3 and 4, they were supposed to be the same, but we actually had one failing at 3 and at 3.5. The model actually came somewhere in between, and a load capacity of 3.2. Okay, so just moving on to a more practical example. This is a 2.2 meter span culvert with partial ring separation, and the ring separation is shown in black on the drawing you can see on screen now. So the question is, can we model that in the software? I think I've got that one available. It's a very small bridge. Actually, for these kind of size of bridges, then you'll find that applied vehicle loading is quite large in relation to the self-weight of the structure. So they're ideally suited for solving using a mechanism type method, such as the ones used by Ring. For very long span bridges, you'll find that the applied load is small in relation to the self-weight of the structure. So actually, use of a program like Ring is not that useful. You normally find other issues are more concerned to the assessment engineer. Okay, so what I've did then is I opened the file which has already got lots of pre-built load cases there, and what it's told me is that I've got a minimality factor of 0.3, which sounds low. What I've done again is model the relevant parts of the structure according to the drawing. So we have no ring separation near the abutments, and then we've got ring separation elsewhere. And what I might want to do is see whether or not stitching would be useful, and I could selectively connect these rings together to see what influence that might have on the capacity. Okay. So the last thing I want to very briefly cover is reinforcement. It's one of the less well known about features of the software, but essentially what you can do is you can put in reinforcement either on the extrados or intrados, or actually at some depth. In terms of the method that I outlined, the mathematical method I outlined earlier, it changes it very, very slightly. We now need to take account of a compressive and a tensile force arising from the presence of the reinforcement. But essentially all the other, the rest of the methodology stays the same. Key to note, there are some assumptions. So you assume that the reinforcement yields at a prescribed force in a ductile manner, and it's assumed that you don't get debonding of the reinforcement, and perhaps most importantly, we're assuming that you get a similar global response before and after reinforcement. So it's only really suitable if you have relatively light reinforcement where you're not expecting to get a completely different mode of response and potentially a brittle response. There is a validation example in the literature. There's a 5-meter span soil-filled, a number of soil-filled bridge examples tested by TRL some years ago. So they tested bridges with and without reinforcement. This particular case, the reinforcement was steel reinforcement, so given area and yield strength gives a tensile force of 149 kilonewtons per meter width. The bars in this case were inserted in grooves, so the bars themselves were 19 millimeters in from the intrados, and I've got, I think, a case of the unreinforced bridge here. So it's a multi-ring arch again. So if I click solve, then we have this characteristic mode of response, so multiple hinges forming. What I can do is look at each of the contacts, and I can see initially that there's no option to put reinforcement there. If I go to the main edit bridge dialog, there's a checkbox saying bridge includes reinforcement, and then when I zoom in, you will see there's also some reinforcement properties for every contact. So what I could do is I could go around selecting all of the contacts, but it would be a bit of a pain. So what instead I can do is I can use a select tool to actually select all the contacts in a given ring, and then what I can do is I can enter those values that we saw in the previous slide. So I think it's 149.3 kilonewtons, for the force, and I think the bars were at 19 millimeters in depth. So you can see now we've got the reinforcement shown, and I click solve now. The capacity has gone from 198 to 322, which is pretty much exactly what we had experimentally. So that's 200 and 320, assuming that we've used the right properties. Other things to know is we're now not showing the line of thrust, and that's because the line of thrust isn't particularly useful in this case, because it's going to be outside the thickness of the masonry. We can view it, but you can see the line of thrust for the lower ring is actually outside the lower ring. So in this case, it makes more sense to hide it and to show, for example, bending moments. So we can see the bending moments indicating that we've actually got yielding of the bar in this region here and also this region here. Okay, so as I said, we've got relatively close values to the experimental recorded values in this particular case. Okay, so just to wrap up, support movement mode allows potential load paths under working loads to be explored, and also the likely causes of existing cracks to be investigated. LimitState ring allows local defects to be modelled, for example partial ring separation, but also other things, so cutouts, blocks of different densities. Reinforcement can be modelled, although you need to bear in mind that we're assuming ductility and full strength is mobilised. Okay, so I just got a couple of minutes for questions. Okay, just having a look at the list. If you've got any questions, if you enter them in the box. Can you model different arch shapes? Well, the example of that is probably the best example is the support movement example here, where maybe it's difficult to see, but the shape of the outer span here was it was very badly distorted, and so what we did is we used it was a laser scan, and we used many points and entered those into the software and used a interpolated value, sorry, interpolated profile, should I say. Just time for one more question, possibly. Okay, so no more questions. I'll pass over then back to Tom, who will just wrap things up. Thanks very much.
Thanks, Matthew, and thanks everybody for listening today. We hope you do find the webinar informative and maybe learn something that you didn't know previously. For people who aren't current users of LimitState Ring, we will get in touch with you over the next few days just to get some feedback from you, find out if you have any further questions about the software, see what you think of it. For everybody, also, please do look out for the event notifications that we'll send out via email and post on our website, which is www.limitState.com/events. This will give you advance notice of the upcoming webinars and other events that we may be holding as part of LimitState. So again, I'd just like to say thank you all for taking the time to join us today, and we do hope to see you all again for one of our future sessions. Goodbye.